the idea in trigonometry that's important is to recognize that we could actually represent x and y values by using angles. And so if we were to, let's say that we were to just draw an angle right here. And let's assume that that angle is some angle theta. And of course, we know that angles always start at the positive x-axis and rotate around, right? And so if this is our angle, then remember that we could designate a particular point on that particular ray as being the point xy. And that would imply that I would have to travel horizontally until I get right underneath that point. Okay, and then once I get there, then I'd have to travel vertically. That's ugly. I'd have to travel vertically to get to the point in question here. Okay, and so obviously the vertical would be our y value, the horizontal would be our x value. Okay, but that seems like a really stupid way to walk if I'm just trying to get from the origin here to that point. Why would I walk x and then y when I could just turn my body and then walk out a certain amount? We're going to call that r, simply because of the fact that it is a radius of a circle. And that is a horrible circle. But notice that that's really the reason why we're calling it r. We're just calling it r simply because of the fact that it is a radius. And so if we were to look at this in terms of trigonometry, we can recognize that there's a couple of relationships here, right? We should see that x, or that if we were to look at cosine, if we look at cosine of theta here, cosine of theta is the adjacent side over the hypotenuse. And likewise, sine of theta is equal to the opposite side over the hypotenuse. Which also demonstrates that if r happened to be 1, meaning I was on the unit circle, that's why cosine of theta would simply be just x and sine of theta would be y. But if it's not, and it's now maybe a radius of 3, now I've got to realize that x is equal to r times cosine theta, and y is equal to r times sine theta. Which now implies something really important about our graph. That point xy can actually be represented parametrically with the equation, or with the point x equals r cosine theta and y equals r sine theta. Okay. Well, that's a really big deal. Because if we wanted to now look at this in terms of walking straight out to a point, let me say that again, the most obvious way to get from one point to another is turn the direction that you want to turn and then just walk out. It seems to be just much more reasonable in terms of how to get to a location in space than walking along the x-axis and then the y-axis. So this is one reason why polar curves or polar representations are often helpful. Okay. So we're going to do an example, though, of being able to graph now a function involving r's and thetas. So let's just go ahead and start by trying to graph r equals 1 plus sine theta. And there are actually two completely different ways of graphing r equals 1 plus sine theta. Okay. One way to do this I think that might work. Yeah, maybe that's a little better. Whatever. So there's two different ways to do this. One way that is totally fine to do, okay? But one way to do this is just to do it like we did in the old school pre-algebra, or if I wanted to graph y equals 2x, I would create a table, plug in a bunch of x values, get a bunch of y values, and then plot them one by one. Well, we could do the same exact thing here, okay? We could come up with a list of r and theta values. But notice that in this case, the independent variable is theta, okay? And so we can see here that if we pick certain theta values, then those should give us the corresponding r values. Okay, so let's just go ahead and pick a few nice ones. Okay, what would be some good, nice values to choose?
0.
0 for sure. What else?
Pi over 2, pi,
Yeah,
stuff like that.
definitely. So definitely my quadrantal angles. So 0, pi over 2, 3 pi over 2, pi, and so on. Okay. Now, if I pick 2 pi, that's totally okay as well. But notice that it's going to give me the same r value as 0 because those are coterminal to each other. So if I plug in sine of 0 is 0 plus 1 gives me a value of 1. So that means when I turn to the angle of 0, walk out 1 unit. Now, if I were to turn to the angle of pi over 2, sine of pi over 2 is 1. 1 plus 1 is 2. That means turn to pi over 2 and walk out 2 units. Now let's go to pi. If I go to pi, sine of pi is -1, or is 0. 0 plus 1 is 1. That means turn to the angle of pi and walk out 1. And now at 3 pi over 2, it's saying to take sine of 3 pi over 2, which is -1. And now I get an answer of 0. And by the time I get back to 2 pi, I'm back to 1. So everybody okay so far with how we completed that table? Okay. Well, we're not quite complete with the table yet because I don't think I really can tell by plotting those points what this is going to look like. So let's try to plot this. And remember, we're still plotting it on an XY graph. One, 2, 3, 4, 5, 6. That should be good. Okay. So let's keep in mind that when we're plotting this on an X and Y graph, we're still thinking about this in terms of the unit circle and where these angles are, right? 0, pi over 2, pi, 3 pi over 2, and so on. Okay. So one thing that I like to do is just think about this in terms of rotation. So as I'm rotating around here, what is my graph going to look like? Well, let's make each one of these values. Let's make this every 3 is going to be 1. And let's make this equal to 2. And let's make this 1. Let's make this 2. And the reason I only have to go out to 2 is because that's the biggest value this could possibly be. This is going to be -1 and -2. But notice it's not quite -1 and -2 in the sense of things because these are radii. We're extending from here outward. So I'm not extending out to -1. So these are also values of 1 and 2. They're just in the direction of pi, right? And these are values of 1 and 2 as well. Okay. So let's go back to our table. Okay. Our table says start at 0 and go to the radius of 1. By the time I get to pi over 2, I'm at a radius of 2. Get to pi, I'm at a radius of 1. Get to 3 pi over 2, I'm at a radius of 0, and then I'm back to 1 again. So let's plot that. Okay. So we see that at the angle of 0, I'm at 1. And by the time I get to pi over 2, I'm now up at 2. And by the time I get back to pi, I'm at 1. And by the time I get to 0 or to 3 pi over 2, it says that 3 pi over 2 walk out 0. So it's hard for me to kind of point to show you what's going on, but I'm saying point in this direction and walk out 0. So what does that mean? Anybody?
It curves back inwards to 0.
Okay, so that must mean that I'm going to plot what we refer to as not the origin, but we refer to that as the pole. As the pole, okay, of the polar graph. So it's kind of like the North Pole and the South Pole. It's the pole of our curve, okay? So everybody see what this looks like? So it's what, just a triangle, I guess, or what?
No, it's a complicated curving shape that starts at 1, curves out almost like an egg on the top half, and then does this weird curving in.
Yeah, but I
W on
can't
bottom.
tell from just 4 points, and that's kind of my point here, is that I need some more points. I need some more angles to plot. I need some intermediate points here. So why don't we start picking something that's going to give us some nice sine theta values? So what are some angles that give us some nice sine values? Pi over 6, pi over 4, pi over 3, I mean, all of those guys, so the unit circle. But what would be the best? Pi over 6, pi over 4, pi over 3? What's sine of pi over 6?
Square root of 3.
Oh, goodness. Okay, so
1/2,
that's
right? It's 1/2.
Because he gets 1/2.
you guys have got to know your unit circle. And if you don't know your unit circle, you better learn it in the time between Calc 2 and Calc 3. Okay? I don't mean memorize, I mean learn it, understand it. What we need to recognize about the unit circle, okay, is that each of the x values are cosine values, which is basically just saying, what is the x coordinate at the point pi over 6? Well, look at pi over 6, how it's got a big X and a small y. X is root 3 over 2 then, and y is 1/2, because 1/2 is smaller than root 3 over 2. But if I was looking at pi over 3, now I could see that at pi over 3, there's a small x and a large y, which means in this case, that means that the small x is 1/2, so cosine of pi over 3 is 1/2, and sine of pi over 3 is root 3 over 2. There are a ton of patterns that show up in the unit circle. I did a big lesson in Calc 3 or in Calc 1 for some of you that chose to stay after class one day. It was ironically the day of those really high winds, and some of you stayed after, and we did a good review of the unit circle. If you don't know your unit circle and you don't understand trigonometric angles and the relationships to sine and cosine, you really need to make sure that you're spending time learning that in between Calc 2 and Calc 3. But make sure that you see the difference though. This is a really big deal in polar curves, okay? So the point of this is that when you're looking at pi over 6 up here, pi over 6 is a shallow angle. Sine is going to be the smaller of the two ratios, so sine of pi over 6 is 1/2. Then sine and cosine of pi over 4 are both root 2 over 2. And then we're looking at sine of pi over 3. Pi over 3 is a steep angle. So the y coordinate is bigger, so that means that sine of pi over 3 is root 3 over 2. So I could plot each of those individually. So if I want to, I could plot pi over 3 and pi over 4 and pi over 6. Okay, but notice why one of these would be better than others. Sine of pi over 3 is root 3 over 2. So if I now add 1 to that, I get 1 plus square root of 3 over 2. Now I've got to get a common denominator to get 2 plus root 3 over 2. And then I got to get my calculator out. 2 plus 1.73 is 3.73. 3.73 divided by 2 is about 1.86 or so. I mean, it was a complicated process to be able to do that. Root 2 over 2. plus 1. Well, root 2 is 1.41. Divide that by 2, you get 0.7. So at pi over 4, I get 1.7. But look at how nice pi over 6 is. Sine of pi over 6 is 1/2. 1 plus 1/2 is 1.5. That's why I'm going to choose my pi over 6 angles. So I'm going to choose pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Okay, so you have choices of what to pick, and I'm just trying to pick values in each quadrant to get an idea about what this graph is going to look like. But why don't we go ahead and plot a few of those? So this is basically now saying that along these diagonals, along the diagonal of pi over 4 and the diagonal of pi over 6 and the diagonal of pi over 3, what are these values going to be? Well, I'm going to go out 1.5. So 1.5 is about this distance right here. Okay, that's 1.5. But you got to realize I'm going out 1.5 diagonally, right? So you got to kind of think about this as a circle about where this would be. So I think that 1.5 is going to be somewhere probably about right here or so. Now let's look at 1.7 at the angle of pi over 4. At the angle of pi over 4, now we're going to walk out 1.7. 1.7 is going to be further than what 1.5 is, but not quite as far as where 2 is, and 2 is going to be this circle coming around here. So it looks like maybe 1.7 is somewhere around here, a little bit further. And then we've got 1.86. 1.86 is going to be, you know, a little bit further, not quite 2. So I don't know, somewhere about maybe like right here. It's hard to tell where it is exactly. But what we should be able to recognize is that as I'm moving from 0 to pi over 6 to pi over 4 to pi over 3 to pi over 2, it looks like it is kind of creating this curve here. Okay, this is, I'm a lot neater on the board at school, so sorry, but you get the idea. Okay, so it turns out to basically be something like that. Okay, all right. But I don't want to have to do that in every quadrant. So that's why I'm just going to go ahead and pick a few basic points to get a general idea of what's happening, and then I'll construct the curve. So let's go to 5 pi over 6. Again, second quadrant. So what's sine of 5 pi over 6?
1/2.
1/2. 1/2 plus 1 is again 1.5. Well, that's nice because that means that the exact same angle in the second quadrant, at the exact same angle, which is going to be a pi over 6 angle, I'm also going to be going out 1/2 or 1.5. So I know that that's going to be somewhere around 1/2, which is going to be somewhere around right here. So it looks to me like it's probably going to be symmetrical because of the second quadrant, sine is going to be exactly the same as the first quadrant, which is why it looks like it's going to continue to go curve around, hit this point, and then come back around and get back to pi. But what else is happening? Well, that's why I can now pick a few third quadrant points. But again, I'm going to base it on symmetry and extend my pi over 6 angles through. And if I do that, then I want to see what's going on here. Well, let's see. If I plug in 7 pi over 6, am I also going to get this point, very, you know, based on the symmetry here? Well, I might, I don't know, but it seems a little weird that if the graph seems to be consistently curving, it seems weird that it's going to go like that and just bounce over there. Okay, So why don't we go back again and try our 7 pi over 6? What is sine of 7 pi over 6?
Negative 0.5.
Negative 1/2. So 1 minus 1/2 is giving me negative 0.5. 11 pi over 6 will give me the exact same thing. So wait a second. What does that mean? What does that mean? Ideas?
Does it mean that instead of 1.5 on the axis, we go to the 0.5?
Yeah, I'm sorry. This is not negative. I apologize. Right? This is negative 1/2. 1 minus 1/2 is 0.5. So, yeah, it's saying point in this direction, 7.7 pi over 6, and just go out 0.5. So in the direction of 7 pi over 6 in the third quadrant, right, here's 0.5. So that's how far I'm going to go out in this direction. And in the direction of 11 pi over 6, I'm going to be going out the exact same amount. I'm only going out 1/2 of a unit. So I think I have enough to actually connect this, because notice that once I get to pi and I move to 7 pi over 6, I continue the curve. And it looks like as I continue to get larger and larger and larger, I'm getting to this point right here. And then I have to continue from 3 pi over 2 through to 11 pi over 6, back to 1. And this is kind of like an upside down heart, which is why this type of graph is called a cardioid. And that's one way to graph, is to just recognize that as you change your angle, there is a consistent change in the radius. It's not a random jump, okay? Turns out, though, that there is a different way that you could graph this, or a different method instead of just plotting random points. And that's by considering the graph of y equals 1 plus sine x. That's basically the same thing that I have over there, you know, r plus 1 sine theta, except that this is now considering basically describing my r, and x is describing my theta. So let's go ahead and just graph that from 0 to 2 pi, okay? So okay, so let's say that 12, perfect. So let's say that this is 2 pi. Half of that is pi. Half of that is pi over 2. Halfway in between here is 3 pi over 2. And there we go. So how do I graph y equals 1 plus sine x? How do you go about graphing that?
So we know what the graph of sine x looks like. It's just kind of a curve that goes up in the positive quadrants, like quadrants 1 and 2.
Yeah.
And then quadrants 3 and 4, it's below the x-axis. But since we have a +1 there, we can think of that as a vertical transformation.
Very good, Abby. Perfect. So we just realized that it's the same as the graph of sine x, except that now instead of sine x that normally starts at the origin and goes up, then down, then up, now we realize that it's going to be starting at 1. So let's say that 1 is right here. So there's 1, there's 2. And so if we were to graph this, then this would start 1 unit above where it is, and it would end at obviously the same place, and halfway between it would hit the same place. And I know that it's going to start by going up, and so at halfway between 0 and pi, it's going to reach its maximum. But then notice by the time I get to 3 pi over 2, it's got to go down the same amount, which means it's going to go down to 0. So now if I were to graph the curve, I could see that it starts here, flattens out to here. That's the highest it goes. Then it comes back down to pi. Then it comes back at 3 pi over 2. It's now at 0. And then by the time it gets to 2 pi, it's back to 1 again. And now what we're doing is trying to merge or basically transform this onto a graph that essentially looks now like a graph of concentric circles. So before we do this, okay, I just want to go to Desmos real quick here. And I want to graph r equals 1 plus sine theta. So what I've done here, if you want to do this on Desmos, you go to graph settings and you could change from your regular grid to polar curves, okay, or your concentric circles. So when you do that, notice that all that's happening is that you're now changing. You're now realizing that the grid has no x's and y's. It has no rectangles anymore. This is just a matter of concentric circles with a radius of 1, a radius of 2, a radius of 3, so that I could really just count out in all of our standard directions. So we already saw what our graph of r equals 1 plus sine theta looks like. We graphed it earlier, and that's how it looks, right? But let's think about how we can actually change this by looking at it in terms of an xy graph. All of the information that we have up here is now shown on our graph. We can see that at the angle of 0, I'm going to start at 1. And I know that my r values are going to increase until I get to 2. So doesn't that mean that as I start working my way around, that these these radii are going to have to increase as I move around? They're going to have to increase and increase until it finally gets to the furthest away at 2. And now they're going to be the same exact r values, only in the second quadrant, because we're now from pi over 2 to pi. This is quadrant 2. And so that's why whatever happened on the left side is going to happen, or on the right side is going to happen in quadrant 2. Which is why by the time it gets to pi, I'm now at 1. By the time it gets to pi, I'm now at 1. And now I can see that my radii are getting smaller. They're getting closer to the pole until they finally hit 0. All of my radii are getting closer to the pole until it reaches 0. Which is why every angle you draw, no matter what angle you draw, you should realize that the values of the radii are smaller and smaller and smaller and smaller until it finally gets to 0. But notice the symmetry. We could see that this piece in the quadrant 4, because 3 pi over 2 to 2 pi is quadrant 4, is going to be the same that happened in quadrant 3. So whatever happened in quadrant 3 is going to be symmetrical over here, and that's why this is our answer. 2 totally different ways to graph. It doesn't matter which one you do, just know how to do it. Okay? So that's really just all the recap I'm going to do from polar curves. But does anybody have any questions or confusion on anything? Or maybe you want me to reiterate something from trig that maybe you've forgotten, or anything? Anything you want to chat about?
On the cardiograph, for the 1.5, the pi over 6, why did you graph it like a little bit, like between 1 and 1.5?
That's a great question, because you're wondering, why did I graph at 1.5? Why did I graph it more at, like, I don't know, 1.3? Is that your question?
Yeah.
Yeah, and the reason is that this is not an x value of 1.5. It's a distance, and I wish I could put my, so if you look at my picture, I put my fingers at what 1.5 units away is, and then I just put that distance on the line of pi over 6. So it's really just basically saying that If this right here is a distance of 1.5, then I need to go that distance in the direction of pi over 6. So those two blue lines should be the same distance, right?
Yeah, that makes sense.
And that's the idea. So they're graphing radii, not x values. So
Yeah.
I just put the 1.5 right here to tell myself how big is 1.5, so that then I could put that along the indicated line. Okay. Anybody else?
So if on an exam you told us to graph, like r equals 1 plus sine theta, would we have to do it like the polar graph, or can we just graph it as like y equals 1 plus sine x?
Great question. This is the polar curve. This is a rectangular curve because we're in the rectangular coordinate system in terms of x's and y's. So this is our rectangular curve that's just helping us to plot our polar curve. So r equals 1 plus sine theta does not look like this. That's what y equals 1 plus sine x looks like. R equals 1 plus sine theta is this graph. That is what's necessary. So basically all I'm saying is I could use y equals 1 plus sine x. Since we know how to graph that from trigonometry, I can use that to help me to create this graph. It was already drawn, but I basically could have started from scratch by just saying, let's plot at the coordinate of, at the angle of 0, plot 1, at the angle of pi over 2, plot 2, at the angle of pi, plot 1, and at the angle of 3 pi over 2, plot 0, and at the angle of 2 pi, plot 1. And then I could see that the radii increase in the first quadrant, the radii decrease in the second quadrant, the radii continue to decrease in the third quadrant, and the radii increase in the fourth quadrant. So this graph, y equals 1 plus sine x, is just helping us to construct this graph over here. So this is the graph of r equals 1 plus sine theta.